This
Hello
call
all.
is now being recorded.
Hello all. Every moment is a fresh beginning. With that, we are here to make your good day as a great day. With very pleasant good morning to one and all present here, I welcome you all to the CIT Quantum Hackathon 2022 workshop series sponsored by IBM Quantum as a part of Quizkit Fall Fest. First of all, congratulations to all the participants for stepping forward to join us because I think participation is more important than winning a competition. All the best and wish you all success. Are you guys ready to jump into the world of quantum computing? And yes, finally the day has arrived to explore new things and gain knowledge. It's my privilege to welcome our honorable chief guest and speaker, Dr. Shesha Ragunathan, senior research scientist in IBM Quantum. About him, he has completed his PhD in electrical engineering, quantum computing from University of Southern California, Los Angeles in 2010 and joined IBM in 2011 as a part of Electronic Design Automation EDA timing analysis development team. Since 2018, he has additional responsibility of being IBM Quantum Ambassador and now a Distinguished Ambassador plus Technical Ambassador, and he is our Asia Pacific Geo Lead for the program. Sir, once again, I welcome you and extend my sincere gratitude for you for taking your time to share your quantum knowledge and experience. We are so thrilled to listen to you on the topic of quantum algorithm in near-term quantum computers. The session is all yours now, sir.
Thank you all. Hope you can all hear me.
Yes.
Um, all right, let's get started. Uh, I'm getting a echo. Okay, now it's better. All right, so I'm going to talk about quantum algorithms and the near-term quantum computers. So I'm looking at uh, about 45 minutes or so of presentation, and time permitting, I'll show some of the source code or coding. And many of the folks in this audience, at least I'm sure, will be aware of that. But nonetheless, let's see how it goes. So primarily, the near-term quantum computers are interesting. What does it mean? So near-term quantum computers are quantum computers that are available today, which is a relatively smaller number of qubits, which can be somewhat noisy. How do we use those devices to the best possible level? And that's the question. That's the challenge of near-term quantum computers. So the algorithms, quantum algorithms in the context of smaller machines in terms of qubits and also noisier machines relative to the fault
ठीक को
tolerance
सुना अच्छा
requirements.
looked up here.
Sorry, was there a question? Okay. Um, so that's what will be the focus of today's discussion. So why variation quantum algorithms? So if you see the broader timeline, and this I want to indicate is just a cartoon timeline to indicate some of the key broader uh, time changes, shifts in the overall scheme of things. So if you see the initiation of quantum computing in the normal or modern terms since 1981, through to about 2016, I'm generally broadly classifying it as experimental, where the idea was you have the theorists proposing quantum algorithms and the experimentalists in their labs trying to perform certain experiments and say that you can do those algorithms in some limited extent. So some proof of concept, toy examples, and demonstrate that working. 2016 was very important because that was the year when IBM put its machine on cloud. That changed things dramatically. Now, what that meant was that now the machines or the hardware that were accessible only to typically to a physicist or an experimentalist was now made available broadly to the wider audience. Insofar as programming goes, now you had a wider audience who could now program an actual hardware and see it work. And that was a completely transforming event. And then later, you had open source platforms like Qiskit that had came about on top of these hardware that sort of opened up the overall programming stack. Now the programming stack has evolved quite a bit, but what is important is now we have gone into the level where you can now program this hardware, and more interesting algorithms and research techniques have come about. In 2017 or 18, John Preskill um, labeled labeled a term called NISQ, Noisy Intermediate State Quantum. At the time of naming, the best machines that we had were in the order of 7 qubits, 10 qubits, 7 qubits to 14 qubits or so. So he was talking about 50 to 100 qubits as the regime for NISQ, but now we are way past that one already. But the terminology sometimes holds. But I'm just calling it near term. Instead of NISQ, I would want to call it near term machines, where what these machines are they are not fault tolerant. They are not as clean as fault tolerant implementation, but they are becoming stronger and stronger in terms of its capacity and powerfulness. So we are, in fact, when I created that chart, it was 2021. So we are in 2022 now. So we are well into this regime of near-term computer that is way beyond the small proof of concept toy machines. Now we are in the 127 qubits, and we are well in the way of having 433 qubit machine this year sometime. So in this regime, how do we program this? So we are far from having a fault-tolerant computing. So all the original traditional algorithms were developed based on fault-tolerant based machines. Now we are not in that regime. However, these machines now are stronger and powerful. So what do we do with this? So if you go back to the history of quantum algorithms, this is again a broad snapshot and not meant to be exhaustive by any means. Shows some of the trajectory. If you see, in the early 80s was the question of, is quantum computing different from classical, and if so, how so? So there were many sort of thought experiment type examples that came about to look at it. In the 90s is when the transition slowly moved towards solving real problems of interest, not abstract mathematical problems to demonstrate certain differences in terms of computational capabilities. So if you see all these algorithms that came about in the 90s through the 90s, the most important, of course, is Shor and later Grover. All these were developed assuming that you could implement the algorithm exactly in a quantum hardware. If you move further into to 2010s, you would see that a couple of important algorithms happened. The variational quantum eigensolver and QAOA both came in 2014. Both are a type of algorithms which we will talk about today is called variational quantum algorithms. They are very different from the ones that came traditionally, where it was completely quantum. All the algorithm was completely quantum and self-contained. Here, it was not so. It was a hybrid algorithm. And this form factor of these algorithms, the way it was structured, was very important and different. I'll talk about that shortly. And as you can see, 2016 is when IBM put its machines on cloud. So that changed a lot of things. And whole lot of application came about leveraging these algorithms, this basic framework of variational algorithms. And a lot of applications based on these came about, including QML pricing, battery optimizations, and many other optimizations and machine learning techniques have come about subsequently. So now we are well into an era where variational algorithms, and some of them are even talking about post-variational, but nonetheless, variational will continue to be an important technique in this era and for some foreseeable future. And it's important to understand what these algorithms are and how do we use them. So today I'm going to talk a little bit about that. But before I get into the variational algorithms per se, let's look at the quality of the machine. I'll make a quick comment on that. This plot is on the superconducting qubit technology, which is the one that IBM uses. It sort of shows you the lifetime. Lifetime here refers to the qubit's lifetime to hold a state. If you have something a quantum state available, how long can it hold before it decoheres into a random noise? So if you see from 2000 to this dates to about 2020, I think. And mind you, the lifetime is in a log scale, which means that linear here means it's exponential. So the lifetime is increasing quite rapidly. Now, at the time of this paper was published, it was hovering around anywhere between a few tens to 100 milliseconds. So you can see that it's 10 power 3. This is microseconds. So we are in the regime of few milliseconds. Well, 100 microseconds plus. Now, uh, uh, what is important is the trajectory. So it's increasing exponentially. What these specific technologies are less relevant, more irrelevant is that lifetime through which those technologies can live. Recently, and this was somewhere mid last year, you can see that IBM put out that we have crossed the millisecond barrier. So this was hundreds of microseconds. If you see the latest machines, it will be in that regime, hundreds of microseconds. And this is an experimental device that was done internally. And you could see that now we've crossed the millisecond barrier, and soon this will show up in the production devices too. So you can see that this quality or the lifetime of these devices are increasing and increasing quite bit. And therefore, that gives us more power in terms of doing more compute in that lifetime. So as of last year, when the snapshots were taken, 127, so we had 27 qubits as the big one. We also now have 127 qubits as the biggest machine that is currently available. You guys can go to the same link here. You can access the more latest data there. What I wanted to comment on though is some of these things in green and orange. So the green, you can see that this Mumbai machine is 27 qubits. What is important is quantum volume is 128. Now we have in 512 regime, I think. But this particular machine had a quantum volume of 128. What is important is on the right, the errors. So what you have here is that, let's start with the time. So I commented about the lifetime short just prior. The T1 and T2 are the lifetime. There are two different measures of time. This is the decoherence time, the other is the dephasing time. So you can see it's in the order of 100 odd microseconds. Um, and in terms of readout errors, so this is the errors, C naught, the 2-qubit gate is the gate that has the highest error. So what this error means is that the rate of the number of times a C naught gate would do wrong on a given, say, 100, think of it as a percentage type thing. It's less than 1%, it's going to be erroneous. And the readout is probably more dominant in terms of the error. It's in the order of 1% to 3, around 1% now, I think. This is again a little dated. So what is important is these make it, this is what I mean by noise. So you can see that noise, managing noise is very important. How to leverage these machines effectively while in the presence of noise becomes the challenging part. And here are other two machines with a similar capacity. You can see all three are 27 qubits with 128 quantum volume. We have more advanced machines now on the cloud, but roughly you will see in this regime as of last year, you could see the errors were comparable. We were in that 100 microsecond regime. The error rates were hovering around, about 1% or so, less than 1% for C naught, and readout was the dominant error in all of this. So you can go look up this particular link for all the machines. You can click on them. You can see all these things just the way I have taken these snapshots, and you'll learn more about. There are more information. In fact, you can go look at all the other machine characteristics of these devices. That will give you more insight about those devices. Okay, so the important question now is, what is the best technique to leverage these hardware that are evolving currently? The fault tolerant is still many years out. We would want to leverage this hardware. The important thing is the capacity is also becoming improving. The quality of the hardware is improving. The lifetime is increasing. And the number of qubits is crossed the 100 qubit barrier. As you may know, on a general case, simulating quantum computing algorithms beyond 50 qubits or so is extremely hard in classical. There are specialized cases where you can simulate for a lot more. So we are already in a regime, practically speaking, where it is beyond what you could do classically. So if the only thing that is limiting us right now is the noise. So in the noise, the quality of those hardware is also exponentially improving, which means that at some point, you're going to have some technique that will come through that will leverage the hardware the best possible way, and you will not have classical computer be able to match up with that. So we are already getting into a regime where you cannot do all these things classically, but noise being there is what is holding us back. In time, we're going to overcome that, and that will make it an interesting space where we are not quite fault tolerant. However, the quality is reasonably good enough. There is enough horsepower to be able to do something very interesting beyond what is classical, and therefore variational quantum algorithms become important. So what is the broader structure of variational algorithms? So as I mentioned earlier, the idea is actually this idea of VQE, the original paper that came about, comes from the machine learning space in general. But the idea here is that you have, it's a hybrid classical quantum algorithm, which obviously means there is a classical component and there is a quantum component. So think of you have training set, you have the cost function defined, and ansatz. Ansatz is typically an initial estimate. So that goes into the quantum side of it. So the algorithm essentially is you have a cost function C where the parameter is theta. You have the ansatz or a parameterized quantum circuit that does certain calculation that feeds into this cost function. I'll define what these are shortly. The classical optimization algorithm optimizes for this parameter space such that you have minimized the cost function. You find the minimum that the cost function can obtain and therefore solve a particular problem. This is a classical quantum hybrid optimization technique. So what are the building blocks? So on the left, so we're going to go one by one. So cost function. So cost function is typically, in general, has this form factor. So rho k is the state at any particular point. You have u of theta, and u of theta, um, hold on, u of theta is the one. So imagine this quantum operation to be a u of theta. So you have this u of theta followed by an observable OK, and trace of that is expectation value of that observable on that state. So at the end of u of theta, you get a state out. Think of it as rho k of theta, which is the state at that point in time. And you observe that using O of k and some function f on that observed data. So when you do an observation, that's basically the result that you get here. For simplicity, I've said it as C of theta, but there is some post-processing that will happen beyond the quantum, which I've sort of abstracted that within the green box, but actually that's a classical calculation, which is what this summation is. You do some function of an expected value of an operator or an observable, and you have the cost function defined thus with a number of different operators. Okay. So what are the desirable criteria for this objective function or the cost function? One, obviously, is it has to be faithful. So what it should mean is that if the minimum, minimum or maximum, you can always represent all the problems as a min problem. So the minimum, if I minimize the cost function, it should necessarily minimize the overall problem that I'm trying to solve. So that should be the faithful part of it. So the other part is it should be efficiently estimatable. So this part, the one inside the trace, which is the expectation value of this I should be able to realize it. Now, if it's going to be a deep circuit like our regular or traditional quantum algorithms, which is not implementable in hardware, then that's not useful. So it should be estimatable. It should be realizable in a shallow quantum circuit. By shallow, what is meant is the depth of the circuit. So every circuit in a quantum circuit has, you have the bunch of gates. What is the layers, the number of layers of those quantum steps that are taking place, and that tells the depth of the circuit. And when I say shallow, that shallow says that I have reasonably shorter depth. And the reason for that is again noise. If I have a quantum volume of 128, for example, that means that I can go 7 level deep efficiently. I can't go beyond. If it crosses beyond, on average, the noise is start going to dominate. I can't estimate with greater than 66% of the time. So I need to be less than that. As the quantum volume increases, I have more and more depth to play with. But if you see the depth, that still is shallow compared to the depth required to implement the full-fledged quantum computing algorithm, the traditional ones. And of course, operationally meaningful is obvious. Trainable. So the parameters theta should be trainable. So all these are requirements for this cost function to make sense. So what exactly do we implement? The u of theta, the ansatz part. There are many. This is an active area of research. It's not a solved problems by any means. But broadly speaking, there are two broad categories of ansatzes. One is problem-inspired ansatz and problem-agnostic ansatz. Now, the problem-inspired ansatz, if you look at in, say, quantum chemistry, for example, there is a rich research over a period of last 60, 70 years of understanding quantum chemistry with a lot of techniques that have come with a lot of understanding of some of these approach. So if you especially look at those spaces which are well studied over a long period of time, a lot of techniques have come about. So, and they have a lot of approximate techniques that they have emerged subsequently. And therefore, there is a better understanding of some of those systems and their working. So the ansatzes that are tagged to a particular problem domain, and there are ansatzes, for example, USCC, USCCSD, and such coming from quantum chemistry, you can term it as problem inspired. On the other hand, there could be problem agnostic. Some circuits like the various feature map, the ZZ and other things, which are generally categorized as hardware efficient ansatzes. They come under the problem agnostic space. Problem agnostic because there is nothing specific from a particular application domain that is encoded in that particular ansatz. It's generic. And so you can use either of them. The advantage of problem agnostic, typically, and by problem agnostic here, I refer to hardware efficient, is because the advantage is that it can be implemented efficiently in hardware. While the traditional ones, many of them are hard to implement or very inefficient to implement in hardware. That's the plus. However, the minus is, can it really solve the problem of interest? That's another question mark. So all this requires, and therefore this is a very active area of research. New answers, there are many
Sir,
categories of answers that
sir,
are proposed. Yes.
sir, I wanted to ask you that then this
Can you
problem
hold the
inspired.
question till
Yes, sir.
the
Yes,
end of
sir.
the,
Yes, sir.
can you
Yes, sir.
hold, yeah,
Yes,
can
sir.
you just hold off the question? I'll stop at appropriate time. I don't want to stop. I want to finish the flow and then I can take questions. Sorry about that. All right. The next step is in the optimization process. The other thing that you would need in the optimization is while a cost function is happening, you need to evaluate. So you have this cost function, once you have the trace taken and you have the value of function, it gives a value in the classical real space, right? So you have a space which you're trying to find, say in this case, if it's a minimum, you're trying to find a global minimum, for example, which means you need to know which way to go in that higher dimensional space that we are in. So, which means that you need to know which way to go. Do I go left, down, straight, north, south, east, west? Typically, this is done using looking at the gradients. Which way is the cost reducing? And I want to go that way. So implementing the gradient part is just as efficient. There are gradient-free algorithms as well, the optimization techniques, but here I'm referring particularly to the gradient version of it. Most of the research uses gradient ones, but there are gradient-free techniques too. Amongst the gradient ones, the implementing gradients or calculating gradients becomes an important one. And what is interesting is that in this space for using the parameter shift rule, the gradient calculation is much simpler. It's not very complicated to do and is reasonably efficient to implement as well, because you can see that the form factor of it is very similar to the cost function. If I can do the cost function well in terms of quantum circuit, I should be able to implement the parameter shift rule as well. Finally, the classical optimizers. Remember, there is a classical part as well. So these three are related to quantum part, and the last one is the classical part. So how does which classical optimizer does well? So there are many challenges there. Of course, classical optimizer in this space in machine learning, classical machine learning, everybody is aware of barren plateau being an issue. On top of the Barham plateau are quantum specific things that come into play, hardware noise, and the number of measurements that are needed. So in this case, the operators, the observables that are there. There are many classical optimizers that are there with varying features, which offer different interesting things. Um, so the ones that are most widely used are there are Kobila and others, but SPSA seems to be an interesting. The reason for that is SPSA, you just need to do two measurements, 2 points in order to do that do the calculations and figure out the next steps involved, and that makes it efficient. If I have to do many of these things and if I have to run a whole lot of calculations on quantum hardware, the odds are that somewhere you're going to have an issue and you're going to hit a barren plateau and it's going to be harder. So the lesser number of calculations you need to do with quantum, ideally that is better. So it's always a trade-off between the precision and how much of step size that you would want to do. So each optimizer has its own characteristic. What is interesting is we need to be aware of what each of them bring to the table and what that means to that specific problem at hand and specific cost function and the implementation and the observables that come out of these things. Let me finish the challenges and I'm going to pause for questions. So let me finish this chart and then I'm going to stop. Okay, what are the challenges? So you can very well see some of it comes from the natural classical technique itself. Barren plateau is a big challenge. So what will happen is that if the derivative, if it becomes exponentially small. So the challenge is that in quantum, while the exponential state space is a blessing, it can also have an impact on the Barrett plateau, which also means that if my answer is in one small area in that space, getting to that point is harder. The odds are that I may have a vanishing derivative, which means that I get a plateau, I don't know which way to go. I need to have much finer resolution for me to navigate, which means I need to do a whole lot of quantum stuff, which means that becomes impractical. So dealing with barren plateau is a challenge. And there is a lot of research happening on how quantum computing, how variational algorithms, what are the different techniques to avoid barren plateau? How are there certain answers that are better in avoiding certain classical optimizers? Is it better in avoiding barren plateau? And it's also a function of a particular problem at hand. So all these are very active area of research. The other is the answers. I mentioned this earlier, and the strategies. What's the initial state of the answers, and how do I get started? Remember, we are optimizing for the parameter theta. This is a parameterized circuit. If I have a good starting point, then I could quickly converge on the right parameter set. But if my starting point is not very good, then it's possible that I may degenerate towards a barren plateau. I want to avoid the barren plateau. I want to be in this interesting space where I want to find the minima. So choice of ansatz and the initialization strategies become important. These are all still active area of research. Second is the category of efficiency. So the observables. So here OK stands for the observable. So this is a generic observable. Ultimately, you have to run this in physical hardware, which means it's need to be translated to something that I could do and I could measure. So which means that as you know, in a quantum hardware, the measurement is in the z-axis, the 0, 1. So everything needs to be translated in that. So you need to translate it into a string of Pauli matrices, where Ci is the classical value and sigma is the Pauli matrix. And this is what we can physically implement in hardware. This needs to get translated. So it means that if for one OK, if I translate it into summation in physical implementation, I'll have to have expectation value of each of them, add them up to get the expectation value of OK. So which means all of this translates to so many different runs in the actual hardware. So there are various approaches here. Naturally, you can think of simple things like, so if the observable, for example, has a sort of, it's not uniformly distributed in terms of the Pauli matrices, but some of them are more important. If the prefix or the coefficient is much higher than some of the others, then the impact of that expectation value on the observable's final expectation value is higher. And if it's very small, then the impact of that is going to be much lower. So you can have a simplistic cutoff type thing. Many a times that may or may not work in the case where if it is very strongly skewed towards one, then it works out fine. But if it's not as skewed, but if it is somewhat distributed, you need other techniques. So there are other mathematical techniques used like commuting and non-commuting to reduce the number of these variables. So these are techniques that are, again, an active area of research. You want to have as less of this as possible, and therefore you'll have to maximize the quality of the results that you get out of the quantum hardware. Finally, the accuracy. So what is the impact of hardware noise? So noise generally means that you have the training, for example. If you have more noise, the training, it becomes slower. In fact, it becomes much slower. At some point, you're not going to train much. But the point is, the noise also is secular in taking you away from the problem and towards barren plateau. There have been some results indicating that noise induces and increases the chances of getting to barren plateau. So, and also noise impacts the quality of the result, the final cost value, the function that you get out, the cost function evaluation. If it is erroneous, the decision that you make subsequently based on those erroneous data is likely to cause problems as well. So then there is this approaches that have come to improve this. Error mitigation is one very important approach that has come in the recent past, both in the measurement, in the gate, and other techniques that are constantly being looked at. And these techniques, of course, improve the quality. You're trying to compute, for example, you could have two noisy data sets, two noisy results, but using the two noisy results, if you know the noise that was added, for example, you could do another calculation with an additional noise. If you have that, based on much, you can extrapolate to a zero noise value. What is the potential zero noise value? And therefore get a more accurate result based on two noisy results. So there are zero noise extrapolation technique. There are many other active areas of research that is happening in the error mitigation space in order to contain the quality of the results or to do a better job of estimating the quality, the right results in the framework. Um, Let me stop here. And there was a question. I'm open to taking questions now.
Yes, sir. Mm, you said that for answers there are problem inspired and problem agnostic type of answers. Now, for chemistry, the problem inspired answers is used, but problem agnostic answers are hardware efficient. So, can we use hard problem and agnostic answers there instead of problem inspired?
Of course, they do use problem agnostic ansatz in the chemistry problems. The question only is that, in fact, a lot of current research in quantum chemistry does try to use a problem agnostic. Ultimately, the result is in the is what kind of quality of the results that you get. Can you get the least energy that you could get otherwise from the other techniques? So typically, people try out different techniques, problem inspired as well as problem agnostic, and then see what kind of results you get. So what is our ultimate goal? We should be able to get map the cost function, and I should be able to, in the case of quantum chemistry, have a good view of the energy landscape that we are trying to map. And we will see a little bit of that in VQE that I'm going to discuss shortly.
Okay, sir.
Any other question? All right. So there are many derivatives of the. So all of them have the same structure. All the things that I've mentioned here are derivatives of the basic idea of variational quantum algorithms. What I described just now are the concepts involved in variational quantum algorithms. The first two ones are the ones that are highlighted in green: the variational quantum eigensolver and the quantum approximate optimization algorithm. But subsequently, you have various versions of this in different application domain based on the application requirements. They're called so many other things. And it's a vastly expanding area. And it has different lists in different application areas. I've shown here chemistry, physics, and QML. And there are many others beyond this as well. The potential use cases, it's a wide landscape, but broadly speaking, you have quantum chemistry, material science, or life sciences on the right. You have logistics, routing optimization type problems, supply chain related problems. You have the finance problems coming in, and there are many, many more. Here again, I'm just illustrating some of the potential use cases that have been looked at using these variational techniques. Okay, so let's go to a specific application, which is called a variational quantum eigensolver. As I mentioned, this was one of the first variational technique that came about. So we're going to look at that, and think of this as an application in quantum chemistry space. So given the limitation in time, I'm going to be a little bit, I'm going to go over it a little faster, but hopefully if there are questions, I can address some of the details if I missed in my discussion here. So this is the specific technique, variational quantum eigensolver. You have the Hamiltonian mapping, the initial state ansatz, but you see the core algorithm, it's the same thing that I described earlier. It's a variational quantum algorithm. There is a cost function. The classical optimizer's job, in this case, I marked it E because it calculates the energy. So the classical optimizer is trying to find the minimum energy of the particular system and it's a parameterized quantum circuit, and the parameters set by theta. And the classical optimization is trying to minimize the energy such that you get the right set of parameters set. So that's what is the algorithm. So if you look at it, what are we solving? In quantum chemistry, you're trying to solve a physical molecule, you're trying to simulate a molecule. So a molecule with its electrons and so forth is typically a fermionic problem. One step that you need is to go from a fermionic problem to a qubit Hamiltonian. Just for intuitive purposes, as you know, in all the mathematics that you do, you work in the decimal system, right? You do all these things. But when you actually program it and run it in hardware, the hardware understands only binary. Somewhere there is a translation from the decimal to the binary number system, and the calculation is all done in binary in your computer. And then you get the results back. Similarly, this is a fermionic problem. The description is electron is a type of a fermion. So its description, the Hamiltonian that describes it is a fermionic problem. That needs to be translated into what is called a qubit Hamiltonian. Think of it as a decimal to a binary. You need to go to a Hamiltonian that the actual quantum computer understands. So that's the qubit Hamiltonian. So there is a translation that needs to happen. So fermionic to qubit mapping is what we call it. Then the choice of ansatz. So then once you have the Hamiltonian figured out, so you know what to simulate in the quantum computer, then you need to identify what is the ansatz to pick, that is the initial state, prepare the trial state, ansatz plus the initialization, the theta, and then you go into the classical quantum loop and optimize and find the solution theta star that gives you the minimum. And again, indicate the choice of classical optimizer. The reason for me putting all the question mark is these are all active areas of research. There are techniques to do it already, but that doesn't mean it's a solved problem. There are still explorations happening on various elements of these aspects. So for example, let's take a specific example. So here, let's say you have two electrons that are there at different points. The y-axis is the energy. You're trying to find the minimum energy. Typically, when you have, it's too close, it's always unstable. But there is a distance where it is quite stable. But if it is too far, it becomes dissociated. And that's what these three regimes are. You have the unstable regime where the energy is higher. It drops as you move it away from one another. At some point, it becomes minimum. And if you move further away, it starts increasing because the dissociation energy increases, and then it lands to some sort of a steady state. What typically in quantum chemistry, the problem they always look at are twofolds. One is what is the energy value, and what is the state for which it is the energy value. This energy, the state is typically called as the ground state because that's the lower energy state of the system. It's typically referred to as the ground state. And the energy corresponding to the ground state is called as the ground state energy. So what you're solving for in this equation at the bottom, if you see, is the psi g is the state which has the minimum energy, and Eg is the actual energy value at that particular state. On the top here refers to this fermionic Hamiltonian that I was telling you about. This is in the regime where you're not including the nucleus, but those are details. Those are not so important at this point in time. So you have some description of the molecule that you want to analyze. and you are trying to calculate its lowest energy. And what you're trying to solve for is what is this value, what is the state psi of G, and what is the value of EG. And in order for us to do that, two steps that I described. First, translate this guy, which is the fermionic, to a qubit Hamiltonian. There are many techniques as I described. Typically, Bravi and parity is used. But for initial purposes, you can also look at Jod or Wigner that translates this to a qubit Hamiltonian. It always, by qubit Hamiltonian, it described in terms of polymatrices. Here, it's slightly different with a different physics that you use in the fermions. Um, Once you have that, then it applies this variation. So if you think about variation, where is this variational coming from? The idea of variation, and that comes from this particular specific thing. So when you have a trial state, psi of theta, so imagine you have this loop where you have a classical optimizer setting a theta parameter value to this, and it's then computing this. At any given point in time, you have this, what is called as a variational principle. The energy of this particular state will necessarily be greater than or equal to the ground state energy. And that's called as the variational principle. And that's where the term variation comes in the variational algorithms. So what that means is that, so if you see here, at any point, let's say I was in point here, that was theta corresponded to state here. So I already defined the ground state as the energy, the state where the energy is minimum. And so which necessarily means all the other states are either equal to or greater than that particular energy. That's the minimum energy, right? So if you see here, what this is telling you is that the energy, the normalized energy value is always greater than the ground state energy. And that's the coming from a physics thing called variational principle. And that is leverage. Since this is going to be true, then certain rules follow based on that. Okay, here is the actual implementation. This also in a way addresses the question that was asked a little earlier. So here you have the qubit Hamiltonian that is implemented, that you want to calculate for. So you see, this is the actual implementation. On the box is, think of it as the quantum part, and the blue one is the classical part. And the end of the box, you get the expectation value of a particular observable. The observable has the measurement part. The part that you're seeing here, the psi g of theta, that is the variational circuit, the parameterized circuit. And in this case, the picture that it shows is actually problem agnostic. This was from the paper that IBM published, and this was in the cover of Nature too. So what this one is showing is you have the small boxes here are single qubit gates, and the bigger box is the entangling gate implemented as a collection of CNOTs. There could be different combinations of it, which you will see in the tutorial. And what they had was, this is considered as one layer. So you have the initial encoding, which is the parameters, these things outside this white box. And then you can repeat the entangle followed by this entangle followed by this n number of times. That is the D layers that are coming through, right? And your theta corresponds to the value of theta in this gate, the rotation angle here, 2, 3, 4, 5, 6, 7, 8. So if you see, there are 6, 6, 12, and if you increase the depth, it's going to add 6 more to at each depth, right? But remember, as I described earlier, the more depth it is, you can't do efficient calculation in our current hardware. So typically it is 1, at most 2 depth, okay? And this particular hardware implementation there is no problem encoding that has happened. There is no problem inspired ansatz that is there. This shows a problem agnostic ansatz. However, it could be a problem inspired as well, but the picture shows problem agnostic ansatz because they are more efficient to implement in hardware. So the energy measured, as I described, this picture shows one aspect of it. One calculation gives you one of these alpha values. You need to do n of all these alpha values n number of times to generate the E of theta. That is not shown here in the picture for simplicity, but that's what this calculation would involve. And that comes from the qubit Hamiltonian. What are the observables that you would need, right? So each observable requires certain rotation before you measure, because it depends on the sigma that you are doing and the combination of sigma in each of these qubits. You may have to do certain X rotation or Y rotation and so forth. In some cases, if it is in the sigma Z, then you don't need to do any rotation, then it will be an identity. So this part is the observable side of it on the right. And this odometer type signal is the actual measurement. So here is the trial state preparation I described a little earlier. Um, so, so you have the first portion is the U psi g of theta. This is the trial state that you get at the end of this. And then this portion on the right is the actual expectation value calculation. And there could be D layers as I described earlier. The more higher the number of D, the deeper is the circuit, which means it's going to slowly go away from being shallow. So based on the kind of processor that we currently have and its lifetime and the errors, you can play with the D. In the paper, I think they use D equal to 1. But now I think you can slowly move up to D equal to 2 and higher. So this is the expectation value part. This is the observables. These are the observables. Each of them will be an OK, O of K, that was shown in the abstract discussion in the quantum variational algorithm. And each of them, you have to run the circuit to get the expectation value of this. And then you sum them up to get E of theta. So again, I commented about this a little earlier in the paper, at least in chemistry. SPSA seems to be interesting because you can do only two for every specific thing. The number of calls is only two per iteration, irrespective of the dimension of the optimization. That seems like useful. So this again is a thing that we need to evaluate from time to time. Is it necessary in terms of the current advance in the technology? We probably could do other algorithms efficiently as well. But at the point the paper was written, this seemed like a good idea. And even now, this is by and large a good idea to look at SPSA. However, people do play with the different kind of classical optimizers, not just SPSA, but SPSA is one such technique, particularly in quantum chemistry, that people do look at. So before I go further, any question on VQE? All right,
Sir,
so now,
the example you showed has the problem agnostic answers. For the problem specific or problem inspired answer, as those are hard to implement, so how the circuit looks like in those cases?
you can just implement them because you know what to implement. So if you go look at UCCSD or something, they will tell you what is the unitary to implement. So you just transpile that, you will get the unitary. You can parameterize that further based on which, once you get the circuit, you can parameterize that circuit too. So basically, what is the unitary that you need to implement? What is the state that you need to get to for UCCSD? Those are all defined. You can implement that.
Okay, sir.
The point is, it's not going to be one, right? It's whatever was the technique used for the approximation. Based on the technique, you need to generate that or implement that quantum, the unitary, right? So based on the particular problem-inspired ansatz, what is that ansatz? Means it tells you what state you need to get into. That also tells you what is the unitary that you need to implement. Okay, so in the interest of time, I'm going to quickly give a quick overview. So here is a approach where you're using the variational technique in the ML space. This is the classifier. So here what I'm showing is the variational unitary here. The W of theta is what I described earlier. The quantum parameterized quantum circuit, the same principle applies. You're optimizing for theta. And once that is optimized, you have the W of theta defined. Then you need to, in the variational case, the quantum classifier case, you need to have the feature map part as well. So there are many, many different techniques to do the feature map. By feature map, what is meant is that you have the classical data. How do you map it into quantum space? And then you have the unitary, the variational unitary to go and do these things, right? So as a simple example, you think of, let's say this is a classifier. So a classifier is you are trying to identify a linear, a line that separates two categories of problem. Let's imagine a binary classifier. Let's say the problem set involves the red is one category and blue is another category. The way it is shown in this particular block sphere, there is no line that separates blue and red. You will have a nonlinear curve to separate this. However, if you encode it slightly differently, there is a technique to go for take all the red and map it to the plus state, and all the blue, and you can map it to the blue state, that is the zero state, then you can always find a simple linear space that uh, uh, two-dimensional space that cuts the separates the two easily. So this sort of illustrates the idea. So how do you go from the data set into a quantum space is what this quantum feature map is. Here there are various techniques. ZZ feature is one popular one. There are many others as well. You can encode it in phase, you can encode it in amplitude, you can do various things based on these things. Again, this is again another active area of research. You do this feature map on top of the variational unitary that we described in detail thus far. So you need to do that because you need to get the data into the quantum space, and all the things that we did in quantum variational earlier was all in quantum space. Since in the classifier the data is classical, you need to get it into the quantum space, which is what this one does. And once you have that, you apply this variational one. So once you have the result, you get the results bit string, and the function f of z is the classical bit string. And then based on that f of z, it could map to either 0 or a 1. If it is 0, you can think of it as blue. If it is 1, you can think of it as red. So, but the idea follows the same thing. It's built on top of the variational principle, and this is a variational quantum classifier. The other one in the machine learning space is the generative adversarial networks. The idea here, this is classical, and then I will talk about the quantum equivalent. The idea of generative adversarial network, this is unsupervised learning. So you have the training data, and then there are two elements. Typically in the classical case, both are neural networks. You have the generator and the discriminator. The idea is, can the discriminator distinguish between the data generated by the generator from the actual real training data? And if the discriminator cannot distinguish between the two, then generator essentially in probabilistic sense is mapping the distribution of the training data. And that's what these networks do. In the quantum case, the same thing was extended in this particular work. Quantum has this particular thing, which is aside from the technique itself, there is a other bigger thing at hand, which I want to highlight. Data loading is an important problem in quantum. How do you take the quantum classical data and map it to quantum? In general, is costs in the order of 2 power n gates to make that happen in a generic setting. And that's why some of the techniques like HHL, whilst has exponential speed up, has this problem. It assumes that data loading is efficient. So somehow the problem is exponential, but then without data loading, you cannot implement something in realistic terms. Part of addressing that particular problem is what this research work was about. So what they showed here is they used the generative adversarial network, but then they made it quantum. So what is the quantum part? As you can see here, there are two elements. There is either a generator or a discriminator. So the approach that they have taken is they made the generator quantum. And so what it's supposed to do is generate the data set, data samples. The discriminator remains as before classical. There is no change. So the discriminator needs to look at the data samples coming from the generator and say whether it can distinguish between this training data, the real data, from the artificial data generated by this generator. So this one, in this work, what they did was they did a quantum generator. And they then try to map the distribution. They want to capture the distribution of the data set. And then once you have the quantum generator, generate the data sample that could essentially tell the discriminator, and discriminator cannot distinguish between the real data versus the generated data, then you know that quantum generator is generating the data in an approximate sense, in a probabilistic distribution sense, matches the data set that was provided as input. And when you had that, they then applied that in an application context, which was European call option. This is a specific financial instrument where you buy some asset and then you can sell it in the future. The buying part is the uh, spot pricing, and then you have the payoff, which is the difference between the spot price at time t and the fixed price at the time of buying. The difference is what is the payoff that you have, and they showed that you could implement this. They showed for different kinds of distribution. You could have bimodal distribution, they could have exponential distribution, Gaussian, and so forth. In general, if it is a stochastic process beyond any of the standard distributions, then you end up doing Monte Carlo. There was a paper prior where you could show that Monte Carlo, they could do polynomially faster. But they showed this particular thing, applied the quantum generated or quantum adversarial network in the call option thing and showed that it works in that space. For more details, you can look up this paper that has a lot of information about how these calculations are done. So in the interest of time, I think I'm already over. I'll probably take questions but before I do that, let me summarize. Programming quantum computer in the short term is an interesting space. It's challenging but also equally rewarding time in quantum computing, where we are beyond simple toy quantum hardware to something at scale. We are having things at scale in at least 100 plus qubits, and you cannot simulate them exactly in classical computer. So we are already in a regime where the capacity is beyond. It's just that noise is noise is something that we need to deal with. However, as we evolve, as the number of qubits increases, now we are already beyond what is capable in quantum, so classical rather. As you go to say the next generation is 400, and while each generation is also reducing the noise, so you are likely to get to a regime where you have quite a bit of horsepower or capacity in the quantum space to be able to manipulate and do things much more efficiently than classical. So now we are getting into a very interesting regime where things are beyond what is doable classically. However, since we cannot demonstrate anything real just yet, it's interesting and incumbent on us to go explore this space and these algorithmic techniques to better use the hardware to make sure we get most out of the hardware. And as the hardware evolves and becomes more cleaner and bigger, hopefully we'll get to a point sooner where we have a problem at scale that is relevant that could be solved efficiently using quantum that cannot be done so classically. So whilst I did orient these variational techniques for this near-term quantum hardware, this need not necessarily be limited to this. It may, based on the learnings, as things mature, as algorithms mature, as implementations mature, this will also evolve. And it's possible that beyond, it may even go beyond the near-term era where these techniques gets used in the longer term as well. So interesting times ahead. These are challenging times ahead. As students, many of you would want to look at this as a potential career option and explore these techniques. And I wish you all the best with the hackathon that you guys are getting into. Thanks a lot.
Do any participants have any queries or doubts regarding the session? Please free to feel free to raise your hands if you have any queries. We arrived at the end of our session. I once again thank Dr. Shesha Ragunathan for joining us to make this session a wonderful success. I would also like to thank Dr. Manjula Gandhi ma'am for leading and supporting throughout the process. I also thank Jairani ma'am, Marimuthu sir, and Sudha ma'am for extending your support throughout the session.